So to add any sort of fraction together, what we need is a common denominator. You know this since you studied fractions probably in sort of year 7, year 8, maybe even earlier. So this should be a common idea for you, but obviously algebraic fractions are probably quite new. So I want to write these 3 fractions as a single fraction and probably in its lowest form. So I don't want to end up with any additional sort of terms that are going to cancel down, and if I do need to cancel them. So I'm going to think quite carefully about what my common denominator could be. Definitely need that x plus 1. There's no other way of creating that other than to include the x plus 1 here in my fraction. But when I look at my x and my x squared, the simplest way of writing that is x squared, because the x is kind of contained within this x squared. And now I just need to think about the top of my fraction. So in this first expression, the 4 I need an additional x, and I also need the x plus 1. If I multiply the x on the bottom here, by x and x plus 1, I end up with my denominator x squared, x plus 1. Carrying on then, I get 2 x plus 1 and 3 x squared. If that's gone too fast, check out my video on algebraic fractions. And there is a point to this, so we are getting on to partial fractions. So, simplifying this down, I can't do anything to the bottom, sorry, I'm going to leave the denominator as it is. But the numerator I can expand, so that'd be 4x squared plus 4x minus 2x minus 2 plus 3x squared, and that will give me, when I simplify that down, 7x squared plus 2x minus 2 over x squared x plus 1. So what was the point of all that? Well, partial fractions is just the reverse of that process. So what I want to do is split my larger fraction into a like a sum of smaller fractions. I don't really mean sum because they might not be added together, but a set of smaller fractions that we would simplify into this larger one. So we're basically undoing the process of adding and subtracting fractions to get, and that's what partial fractions is. It just splits it up, your fraction, into smaller fractions. So, thinking about what we had at the start of the last fraction, I could create my denominator from looking at what my fraction is at the moment. So in order to get an x minus 3 in this top fraction here, I must have had a fraction that had x minus 3 on the bottom. And to get this x squared, I must have had a fraction with an x squared on the bottom. But I could also have had a fraction with an x, because this repeat here, this x squared, has x as a factor, and so this one could have been in the equation. And I don't know that it is, I don't know that it isn't, so I'm going to include it for now. Then I also need my numerator, but I don't know what my numerator is. So for now, I'm just going to call these fractions a, b, and c. Now I am claiming that this is equal to the original fraction I had. Hello, there we go. Because I'm not actually wanting to change my fraction at all, I just want to rewrite it. So these two things still have to be equivalent to one another. Now I've just got to go and find a, b, and c. And the way I'm going to do that is I'm going to compare this left-hand side with the right-hand side. And so in order to do that, I'm going to need to have some more commonality between these two fractions. I'm going to need to have the same denominator so I can compare them. So my next task is actually to create that denominator on the fractions of the left-hand side. So that feels a little bit counterintuitive, because the whole point of partial fractions is to split it up into this form. And now all of a sudden we're going back into the original kind of adding up fractions type of thing. But we need to do this in order to be able to create an expression for a, b, and c. So In order to get the denominator of this first fraction to be x squared x minus 3, I need to multiply top and bottom by x, so that the x goes to x squared and x minus 3 to gain that expression as well. My second fraction needs multiplying by x minus 3, and my third fraction needs multiplying by x squared. This now can be compared to this fraction that I've got on my right hand side, because the denominators are the same. So I can in effect ignore the denominators and just consider the equation that's on the numerators of these two fractions. So this numerator then, I've got that a lots of x minus 3 plus b lots of x minus 3 plus c x squared is equal to 5x squared minus 7x plus 3. Now, all I need to do is find a, b and c, and there are plenty of ways that I could do that, but I want to make this as pain-free and as quick and accurate as possible, just because then I don't waste any time in my exam, and I'm not going to be sort of putting any of my accuracy in jeopardy either. So what I'm going to do is I'm going to pick x values. I'm going to pick values of x, and I'm going to pick them so that the maximum effect occurs. And by that I mean I'm going to pick x values so that a, b or c disappear at any given point. Now this is totally legit because I'm not interested in finding out what x is. X is a variable that I can use to my advantage. I'm trying to find a, b and c. So x is 0 would be a good one, because the first expression contains a single x, and if x is 0, that whole thing disappears. The second doesn't contain any single x's, so I'd be able to say something about b. And the third one contains an x squared, which would be 0. So when x is 0, I don't have any a's. I end up with b, or minus 3 lots of b, because I've got 0 minus 3 there. No c's. And then on the other side, I end up with 5 lots of 0, which is 0, minus 7 lots of 0, 0, and plus 3. So minus 3b is 3, in which case b is minus 1. Woohoo, great. Okay, another x value that would be a good one to pick would be x equals 3. Because in this first fraction, we'd end up with 3 take away 3, which is 0. And in b, we would end up with 3 take away 3, which is 0. And so we would just be finding out what c is. So we end up with 0, 0, and then 9c. And that equals 5 lots of 3 squared, minus 7 lots of 3, and 3. Right, so 3 squared is 9 times 5, that's 45, minusing 27, and adding 3. We end up with, what do we end up with? 21, which is totally not right, because 3 times 7 is 21. Whoops. 3 times 7 is 21, and so then that one makes that one 27. There we go, and C is 3. Well done, brain. So C is 3. Now, how are we going to find out what A is? I'm just going to try and move that up a bit. There we go. What are we going to do to try and find A? Well, A didn't come out by selecting x equals 0, and it didn't come out by selecting x equals 3. But those were random values that I picked. I just picked them cleverly. So, in theory, I can pick any other value of x and hopefully find out what A is from that. So I'm going to pick, I don't know, x equals 1, something simple. Let's not be stupid or too ridiculous with it. If you haven't used 0 as a factor, that's always a good one to pick. So, in this case, if I've got x equals 1, I end up with A times by 1 times by 1 minus 3, which is minus 2. I still have b though, because I haven't actually gotten a value that will get rid of it. So I've ended up with a minus 2 lots of b there as well, and a c, and that equals 5 minus 7 add 3. But this is okay because I know what b and c are, so I can just replace those in. So minus 2a minus 2b plus c is 1. And then what are we doing? Minus 2a minus 2 lots of b, which is minus 1. Add c, which is 3. And that equals 1. Rearranging this then, I get minus 2a is equal to minus 4, in which case a is 2. And so the values of a, b and c in my original equation must have been 2 for a, so 2 over x, minus 1 over x squared, so that was b, and then 3 over x minus 3, and there are my partial fractions. Okay, so you're in the exam and you've just performed a partial fractions technique, and in probably 95% of the cases, that's not going to be the end of the question. You're going to be asked to use your partial fractions in an integration, or as part of a differential equation, which I guess is still an integration, but it's sort of tucked inside that, or as a binomial expansion. So there's going to be like loads of different things that you could be asked to do. What you want to make sure is that you're not carrying an error forward. Now, you're not always awarded follow-through marks, so you could potentially lose 4 or 5 accuracy marks, depending on how big the question is, by simply not checking. And that's totally not okay. If you want a top grade in maths, you have to be accurate. And it's not enough to just know what you're doing, you have to do it correctly as well for those high grades. So we need to check. We need to have a method that will ensure that we know we are correct, and that we can carry on with the rest of the question knowing that we're carrying on the correct equation. We've got algebra in here, we've got x's, and we've got an equivalent expression. The left-hand side equals the right-hand side. So if I pick a value of x, let's make it small, I should be able to substitute that into the left-hand side and into the right-hand side and get the same value. When I do this, I get minus 81.0344827, so on and so forth. And then if I pop that into the right-hand side as well, I get exactly the same value, which is great. That shows that I haven't managed, in my process of converting this left-hand side into the right-hand side, managed to change my algebra. A value of x is still evaluating as the same thing on both sides. And so I know that as I take this expression forward into my rest of my question, it is correct. And I sort of think, why wouldn't you check? So partial fractions are an absolutely key skill in your A-level, and when you get questions on it, they will nearly always extend into other topics. So integration, binomial expansion, they're a brilliant way of getting a good number of marks, but you do have to be careful that you're carrying forward the correct answer. So make sure that whenever you get a partial fractions question, binomial expansion coming soon, that you check before you move on to the remaining part of the question. So just substitute in a small value of x.